In this video, I'm going to describe and prove some properties of the orthocenter of a triangle. We're going to use these two examples. The one on the left is an acute triangle. All three angles are acute angles. The one on the right is an obtuse triangle. Angle ABC is obtuse. The first property that we're going to prove is that all three altitudes of the triangle will intersect at a single point. This point is called the orthocenter. In this example, AD is the altitude that connects side BC to the vertex A. Angle ADC is a right angle, and the same applies for the other two altitudes, BE and CF. All three will intersect at point H, which is the orthocenter. For the obtuse angle triangle ABC on the right, BC needs to be extended out to find the intersection of the altitude and the base. In this case, all three altitudes will intersect outside the triangle. Two altitudes will of course intersect, but we'll prove that the third altitude also passes through the point of intersection of the first two. The second property that we want to prove is called the altitude product property. The length of AH times HD is the same as the length of BH times HE, which is the same as CH times HF. In the obtuse angle case, there are overlapping segments, and the same product rule applies there as well. The third property of the orthocenter deals with where the orthocenter lies, depending on the type of triangle. For an acute triangle, it will lie inside the triangle. For a right angle triangle, it will be the vertex of the right angle. And for an obtuse triangle, it will lie outside the triangle. This property follows quite intuitively once we prove the first two properties, which we will do in the following sections. The first proof that we're going to look at is the altitude product result. AH times HD is the same as the product BH times HE. So the proof will apply equally to both examples here, the acute and the obtuse triangle. I'm going to simultaneously highlight both the pictures for you to follow along. So let's consider these two triangles. Triangle AHE shown in blue and triangle BHD shown in magenta. We are going to prove that these two triangles are similar. Angle AHE highlighted in the light blue here and angle BHD also highlighted in light blue are equal because they are opposite angles. And both triangles are right triangles. So the triangles are similar as all the angles match. Next, I'm going to mark the corresponding sides. The sides opposite the light blue angle are marked with a single tick. Similarly, the sides opposite the right angle correspond and are marked with a double tick, and the remaining side corresponds marked with a triple tick. We know that for similar triangles, the ratio of corresponding sides is the same. So taking the corresponding sides marked with the two ticks, we get length of AH divided by length of BH is the same as the ratio of the sides marked with the triple ticks, the ratio HE divided by HD. And now if we cross multiply, we will get AH times HD is equal to BH times HE. The same argument will apply for the third altitude. Also for the obtuse triangle, if you follow along, the exact same arguments apply. Again, the triangles AHE and DHB are similar. So we have proven the first part of the altitude product. Now we are going to prove that all three altitudes of the triangle intersect at a single point. So again, I'm going to use the same two examples, the acute triangle and the obtuse triangle. So I've drawn two altitudes, AD and BE. These two altitudes intersect at point H. We will show that if we connect C to H and extend that to intersect AB, in other words, the line segment CF shown in white here, that segment is also an altitude. In other words, we will show that the angle AFC is a right angle triangle. And the same applies for the obtuse triangle shown on the right. We will prove that AFC is a right angle. Consider the triangle highlighted in purple, triangle BEC, and the triangle highlighted in blue, triangle AEH. We are going to show that these two triangles are similar. First, let's consider the angle highlighted in light blue, angle ACD. Since ADC is a right angle triangle, The angle highlighted in red will be a complement of the angle highlighted in blue. And the same applies for the second angle highlighted in red. Since BEC is a right angle triangle, it will also be a complement of the angle in light blue. Now consider the triangle AHE. Since it is a right angle triangle, the two acute angles are complementary. So AHE is the same as BCE. So now we can see that the two triangles BEC marked in purple and AEH marked in blue are similar because they have exactly the same angle measures. Because they are similar, the ratio of their corresponding sides must be equal. So I'm going to mark the corresponding sides. The sides opposite the light blue angle are marked with a single tick. The ratio of these two sides is AE divided by BE. I'm marking the side opposite the red angle with 2 ticks. The ratio of these two sides will be HE divided by CE. These two ratios must be equal because the triangles are similar. And if we rearrange this, we get AE divided by HE is equal to BE divided by CE. Here I have just swapped the positions of BE and HE. I'm going to highlight this equation in red because it's needed for the next step. Next, let's look at this triangle highlighted in magenta and compare it to this triangle highlighted in dark blue. Again, we are going to prove that these two triangles are similar. I'm going to replicate this acute triangle and highlight the two triangles separately. So now if we look at our equation from the previous result and mark those sides, I have marked side AE with a single green tick. I have marked side HE also with a single tick. Similarly, I have marked side BE with 2 ticks and side CE with 2 ticks. Again, both triangles are right angle triangles. The two smaller sides correspond to each other and their ratios are equal. AE divided by HE is equal to BE divided by CE. So we can say that triangle ABE is similar to triangle HEC. Now going back to the original picture, triangle ABE is similar to triangle HEC. Since side AE corresponds to side HE, angle ABE is equal to angle HCE. Both are marked in white. Now if we look at triangle ABE, it is also a right angle triangle. If the measure of the angles marked in white is x, the measure of angle BAE marked in gray is 90 minus x. Now finally, let's consider the maroon triangle highlighted here, triangle AFC. We have already found that the gray angle FAC is 90 minus x and the angle FCA marked with white is of measure x. What that implies is angle AFC shown here has to be a right angle. So we have been able to prove that CF is an altitude and all three altitudes intersect at the orthocenter.